So let me quickly go through a couple of quick examples using the two equations that we have for circular motion. The two equations are the ones on the left side and the right side. The equation in the middle is just a rearrangement of the equation that's on the right side. Okay, so let's start off using the goal method. So we'll gather all the numbers from the problem and assign them variable symbols. So a horse takes 118 seconds. So that's a time. That's the time it takes to go around one time. So that is the period, capital T. At a speed is v, of 17 meters per second to go around a circular track. What's the radius of the track and what's the horse's acceleration? Okay, so it wants us to find r and it wants us to find a. So now we've done the G step, let's do the O step, which is organizing, figuring out which equations we're going to use. Well, I know T and I know V. So I know V, I know T. So I could use the equation on the right to give me R. And then once I know R, I could plug it into the equation on the left to give me A. So let's do that. So T is 2 pi R over V. I need to rearrange that to give me R. So let's do that in two steps. So V times T is 2 pi R, multiplying both sides by V. And then R is just going to be VT over 2 pi. So that's going to be 17 times 118 divided by 2 pi. And that gives me 319.3 is my number. So that's the A step, the algebra. And then the L step is to look at the number, make sure I've got the right significant figures, make sure the number makes approximate sense. 320 meters. That's probably a good size for a racetrack. It's got to have units of meters because it's a distance. And my problem has 3 significant figures in the number 118 and 2 in the number 17. So I've got to round that to 2 significant figures. So 320 meters will be my final answer for the radius. Okay, so now I know my R as well. Now I can go back and just use the equation on the left to find the last thing they're asking for, which is A. And I know V, I know R, so this is just going to be plug and chug. I don't even have to do any algebra. So V, 17 squared, divided by R. And I'm not going to use the rounded number. Remember, always use your longer number when you're doing the calculation. If I put that in, I get 0.91. I'll round that off to 2 significant figures straight away because I'm not going to need to do any more calculations. And the units for acceleration are meters per second squared. Okay, so the problems for this chapter are pretty straightforward. There's only 2 equations, so it's pretty simple to pick which equation you have to use, and the algebra is very simple. The only other change we can do is to do something where we have to put in a force. So force is mv squared over r. And you see this equation here on the right, it's sort of got 3 steps in it. When you see an equation like that, that means F is equal to m times A. So if you know your A, you just multiply by m. Or F is equal to mv squared over r. If you know v squared and r, then you can calculate the F. So when you see an equation that's sort of ganged up like that, what you do is you choose which part of the equation will give you what you want to find. Okay, so let's do our goal method. So let's see what we've got for numbers. So we've got 1 kilogram, so that's going to be the mass. Model airplane is attached to a string that can provide a maximum tension. Tension is force of 180 newtons. And we'll worry about the maximum word later. If it's flying at 28 meters per second, so meters per second, that must be a speed. So 28 is equal to V. What's the smallest radius the plane can fly in? So we want to know what's R. Okay, so I've got F, M, and V, and I want R. So I'm going to use the part of the equation that I actually have marked right here, that F is equal to mv squared over r. And so r, if I rearrange that, I just flip these two guys with each other, multiply up the r, divide the f, mv squared over f. So now I can put in my numbers. R is equal to the mass, 1.0 kilograms, times v, 28 meters per second, squared, divided by the force, 180 newtons, and I get 4.36. And let's see, what do I need to round that to? Remember that I've done the A, now I've got to do the L, look at the number. I could go to 2 sig figs, 4.4, and it's a distance, so that's meters. Okay, so what does it mean when it asks what's the smallest radius the plane can fly in, and when the maximum tension? How do those two guys relate to each other? Well, you know, the smaller I make r in my equation, F is mv squared over r, so if I make my r smaller, the force gets bigger. So if I'm swinging this model airplane around at 28 meters per second, and I make the string shorter and shorter, what's going to happen is that the force is going to get bigger and bigger. And so if I keep pulling it in, if that force gets bigger than the maximum tension that the string can hold, then the string will break and the airplane will go flying off. So by equating the maximum force of 180 newtons to find the radius, that will be equal to the smallest radius that the plane can fly. And if I make the radius bigger, then the tension in the string will be less than 180 newtons. If I make the radius smaller, then the string will break and the airplane will fly off. Okay, so what I'm going to get you guys to do now is to do this problem. We've got a model train. You're given the mass, you're given the radius, and you're given the speed. And I just ask you to work through these equations to find the period, find the acceleration, and find the force. So you'll just do very similar things to what I just did there.